Oh. Seng 他们有回来吗？什么意思？来了？为什么？反正霸王人有回来，怎么会到机场去？真的是去买水？去Okay, let's start. So good afternoon to everyone. So about your not assignment, project, right? So for the project, I don't want you to just focusing on the theory. I want you to discuss the theory from humanity. So you need to discuss from the viewpoint of the author. OK，从人文的角度来认识这个 theorem。OK， so for example, for example, Ivan and Law Hao pick the same topic actually, is calculus. But uh, but Ivan is do from the point of likeness, and then Law Hao do from the point of Newton. Okay, so you need to do from how they invent this calculus. Maybe they discuss at some point, But so how they claim the theory themselves, you need to spell it out. OK， 所以很期待你们两个人的交锋，好不好？应该会讲一些不同的东西，好吧 ？OK， 虽然你们都是讲 calculus， 但是 Leibniz 跟 Newton 对于 calculus 应该有不同的感受。OK 呢 ？OK。So when you search the how to say, when you search your material, right? Material about the theory, please go and search where the first author thought about it. Okay, when the first where the how the author explained his theory. Okay, no? And how people see it from that author's view. Maybe some person support, oh, calculus is invented by Leibniz, or some calculus is invented by Newton. So what are their view on these two things? Okay, yeah. Okay, cannot. So I want you to study maths through a humanity viewpoint, okay, not just a theory itself. Because most of the theory you guys do, right, already proven or introduced in class already. So I want you to fill in this historical background. Historical. So what's the idea behind this theorem? Does it make sense? Make sense or not? Okay. So yeah, okay. Maybe like next time we'll talk about when should we do it. All right, let's recall what we did last time. Okay, so last time we talked about increasing function, non-decreasing function, decreasing function, and non-increasing function. Okay, and then we relate these monotone or strictly monotone function to their first derivative. Remember or not, in high school, how do you show a function is increasing? How to show a function is increasing? If the first derivative is greater than 0. If the first derivative is less than 0, then your function is decreasing. Okay, this is exactly what we have proven last time. Okay, we proven. Okay, so we proved your high school result. So if f prime first derivative is greater than 0, okay, for every point in the open interval, then f is increasing on the closed interval. So there's a subtlety here. Okay, we don't care about the boundary. Similarly, or dually, if first derivative is less than 0, then your function is decreasing. Okay, and moreover, we put some more result. So what do we mean by stronger? There's an equivalent condition, okay, on non-decreasing condition and first derivative greater or equal to 0. So if f is non-decreasing means what? It could be increasing at some point and then stay static at some point, constant, and then increasing again. Okay, so this is non-decreasing because fx could be less than or equal to fy. Okay, if x less than. So if it's non-decreasing, if and only if the derivative is first derivative is what? Greater or equal to. Okay, greater or equal to. If your first derivative is less than or equal to, then your function is non-increasing. Okay, so you see, second statement is if and only if. Can I prove if and only if for statement 1 or not? Can or not? Can. Try. And if you try, you can't. Okay, there's some. If you try to use proof in proof 2, go back and prove proof 1. So what's the difference between the two statements? 2 and 1. In 2, first derivative can be equal to 0. But in first one, cannot. But precisely of this f prime x cannot equal to 0, we didn't get the converse to be true. Okay. So if you consider the converse of statement 1, what does it say? What's the converse of statement 1? If f is increasing, then the first derivative must be strictly greater than 0. Right. So you think of this statement, is it true or not? Any counter example? Any counter example? So let me write it down. So what's the converse of it? So let's do the converse of this statement. So we swap P. Okay, so this is like first question, right? So first question in our exam, similar type. So state the true value. Proof or disprove it. Okay, so true or false? What do you think? Okay, if you want to guess, what's a smart guess? What do you think is a smart guess here? True or false? Let's say you want to guess, huh? False, because I didn't prove it. Most probably it's false. So let's say you make a choice. Okay, I want to say it is false. So is there a counter example or not? So if you want to construct a counter example, what do you need to do? Find a increasing function such that at some point the first derivative is not greater than 0. So if it's not greater than 0, what could it be? Equal 0 or smaller than 0. Okay, can you find such increasing function or not? Such that there's some point such that the first derivative is not greater than 0. Okay, I'll let you talk with your friend. Okay, for 2 minutes. Can you talk with your friend? Can you create counter example? Okay. Any increasing function come out in your mind? S cube. Okay, good, very good. S cube. S cube consider at which interval? -1 to 1. Okay. So which point? Okay, sorry. A, B should be -1 to 1. So which point in -1 to 1 such that the f prime x is not greater than 0? 0. But f prime 0 is equals to 3 times 0 squared, which is 2. Sense? Okay. Yeah. Okay. So if previously if you want to use the proof of statement 2 to prove statement 1, you will found that in one step you cannot make sure that it is always strictly greater than 0. Okay. Is everyone following this part here? Any question or question? So not greater than 0. Any question? So far so good. Okay. Okay. So last time we started at first derivative, right? So we could continue. First derivative test. Okay. So we will continue looking for our extrema. So what is extrema? Still remember what's the maximum point, minimum point, local maximum point, and local minimum. Okay. So we say that x is the maximum point of f if the value at x is greater or equal to all the fy, okay, for all the y in your domain. Or similarly, we can put a formulation using supremum. Okay, how do we define maximum using supremum here? Okay, so we simply define fx to be the supremum of fy for all the y in df because you are greater or equals to every uh, every um, every value of f on the domain. Okay, similarly, you can define minimum using infimum. Okay, using infimum. Okay. So, is it eligible to write infimum equal to fx or not? Can I write like this? When I write like this, what does it mean? What does it mean here? If I write like this, meaning the supremum and infimum are achieved by the function. Okay, so there's some function value that takes the supremum value or the infimum value. Okay, so if it achieved by some function f, then we will call the. I mean, if it is achieved by the function itself, then we will call the pre-image to be the maximum point. Okay, for the soup or the minimum point for the heat. Okay, if it is achievable. Does it make sense? Okay. For example, what? For example, okay, let's not take example first. Next time we'll see it. And then how about local maximum and local minimum? Okay. So local maximum means it is just a maximum within a local range. So what's the local range here? So we just look at some open interval around x. Okay, if x is a local maximum, local extrema. So how big is this interval? Doesn't matter. Okay, as long as there exists some radius r greater than 0, such that for every point in x minus y and x plus y, fx is greater or equals to fy. Okay, so you know how to picture this statement here? You know how to picture this statement here? So let's write. Let's write this. And then here, let's say we put fx. Okay, maybe let's just take y. Okay, let's say say C is a local maximum point of f. So let's say C is a local maximum point of f. What does it mean? So you need to plot your C at the x-axis first. Okay. And then there exists some r greater than 0. And let's say this is r, this is minus r, this is, okay, let's say this is r. The distance here is r, so you have c minus r and c plus r here. Such that what? Fc is greater or equals to all the f on the point reading c minus r and c plus r. So how does this picture look like? So at Fc here, so let's put here Fc. At this point, this is the tallest point. So within this range, all the value must be less than or equal to. Does it make sense? Yeah, so this is local maximum. So why is it local? Last time I used one example to talk about local, right? So maybe you are locally champion, but not globally champion. So what does that mean? So maybe outside this range here, there will be some point that is taller or greater than you. Make sense? But you can see this maximum point here can be realized as a local maximum as well. Okay, so if you want to be a global champion, you need to be at least a local champion. Correct? Make sense? Okay, so that's why in the local experiment test, we just talk about if a point is a local extrema, then the first derivative is 0. So we are considering all possible maximum point and local. Okay, yeah, so similarly, you can define for local minimum point. Okay, similar construction. Okay, maybe remind us what do we have last time then. So what is let's recall, what is the local extremal test? What's the statement of local extremal test? And can someone tell me what's the statement for this? Right? If what? If f. Okay, if f. Sorry. Okay, if f is so maybe let's put those result run first. So suppose f is continuous, and then do you want to fix any domain or not? Do you need continuity really? Huh? Differentiability? Yeah, what do you need? Okay, you need to differentiate, right? Because we want to talk about first derivative. Okay, so where it has to be continuous, where it should be differentiable. Okay, so I mean, so we can really string our our condition much more general. So what's much more general here? So suppose f okay, so let me do like this. So if f, we're going from the closed interval to Rc, has a local extremum at a point C inside the open interval, and we require it to be differentiable at C. Then f prime C is equal to 0. Okay. So this condition really is our job to find local extremum. Why? Let's say I want to find local extremum of a function. What should I do? Differentiate. Why? 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 Why we differentiate? Where's the logic here? What's the logic here? What's the logic here? Why we will not want to find maximum minimum point? We want to find the zero, the place where the first derivative is 0. Why? Why? Using this logic here. This logic says what? If you have maximum, local maximum, local minimum, then you do first derivative there is 0. So why looking for first derivative 0 will help you find local maximum minimum? Sorry? Use what? What theorem? Rolle's theorem? No. Okay. Logic. Here, logic. If you have a local maximum or minimum, then the first derivative must be 0. But my question is why searching for first derivative is 0 can help you to find local maximum. Mm. Mm-hmm. Sure. Logic. Just here. Just purely this sentence only. You don't need to look for anything else. Just from this sentence only. About 20 works here. Only from this 20 works. Because if this is a if and only if, that easy, right? Because if Q then P. Oh, I found it already. But no, here only if P then Q. But what I claim is still already is your job. Why? This is just logic. Nothing to do with calculus here. Logic only.
I would guess that the derivative is based on us finding the second function.
And then
So if our second is the limit of our second is then there will be change around them.
okay, this is what Low said just now. Yeah, so you listen carefully what I say. No calculus involved here. Just purely logic here. So the question is why, by finding first derivative is 0, what is your job to find local maximum or minimum, or maximum or minimum? Even. Why? Just logic, no calculus. No calculus. Here, the statement is not if P and Q then R. Right? So if you check that R is true, what can you say about P or Q? Huh? No need too fancy, no need too fancy. Very straightforward. No fancy stuff here. Okay. No
Then either not P or
then what? If it is not R, then you must find not P or not Q. But you already found R, meaning what? F is differentiable already. So not Q must be false. Right? So this thing have to be not P have to be true. So if not P true, then what? If X prime C is not 0 and F is differentiable, then that point cannot be a local extrema or local extrema or local maximum or local minimum. So if the first derivative is not 0, you straight away deduce, okay, that point cannot be extremum point. Cannot be. Cannot. So that's why in your high school, the teacher asks you, go and find first derivative equal to 0 first. But I just tell you, if it is not equal to 0, then it is not right. But how about if that point equals 0? Can you say anything about that point? If the first derivative is 0, cannot say, right? It still might not be a local maximum. Okay, so what do you need to do? You need to compare them. Okay, you need to compare them. So from this local extrema point, we deduce what? A corollary. A corollary. So we deduce a corollary here, which is the full first derivative test. Which says that the extrema of f on the closed interval AB can only occur at either the endpoint. By the way, this is not A plus B. Someone said this is A plus B. It's at B. At B. At B or at the points C in AB where f prime C is 0. Okay, so you need to compare them. Which one is the maximum point? Which one is the minimum point? Okay. So if you want to decide whether it's a local maximum or local minimum, what do you need to do? You need to find an R such that it is greater or equal to or less than or equal to all the values around it. Right? You need to do that. You need to go back to the definition. Okay. No? So finding first derivative equal to 0 just help you to reduce down what are the candidates for local maximum or minimum. Okay, if you want to prove that it is a local maximum, minimum, or maximum point or minimum point, you need to go back to the definition. You need to go back to the definition. Does it make sense? Got question? Question or no? No, so you still need to go back to the definition. Okay, good. So, okay, right. So after this, like what Jack mentioned just now, we go to the Rolle's theorem. Okay, Rolle's theorem. What does the Rolle's theorem says? Anyone recall quickly? What does the Rolle's theorem says? If FA equal to FB, then does it see in the interval AB, open interval AB, such that f prime C equal to 0. Good. So how do you remember this statement? So you should remember you have a A, B interval here, and then you have a function f such that FA equals to FB. Okay, so you see here FB not equal, so let's move this B. Okay. And then there exists some point C in the middle of AB such that the first derivative at C is literally 0. So 0 means what? Meaning the tangent line at the FC is, CFC is a horizontal line. Okay. So how do you think about this horizontal line? This is the exact horizontal line that you can connect FA and FB. Okay or not? Okay. So meaning what? So meaning this function cannot be random, This function need to be what? Need to be actually differentiable. Okay, need to be differentiable at the open interval AB. Meaning what? Differentiable implies continuity. So it has to be continuous. Only continuity, differentiability, you can find this kind of point. Okay or not? Does it make sense? Okay. Because I can do stupid stuff. Hello. Welcome back. You see, I can do stupid stuff, What do I mean by stupid stuff here? If it is not continuous, let's say it is not continuous, I also have FA equals to FB here. FA equals to FB here. But what can I do to the middle? What can I do? Maybe I can do something like this. Then there should be nothing between A and B such that the first derivative is 0. Do you agree? Agree or not? Do you agree? Agree or not? And not continuous, I can create a counterexample if f is not continuous. It's 2 here. Make sense or not? So differentiability are really important, or if not, you cannot do the Rolle's theorem. Make sense? Okay. This is about the Rolle's theorems. Okay. And very important, so you cannot simply throw away the condition. Yeah, otherwise it won't work. Make sense? Okay. Okay, good. Okay. So the upgrade level of Rolle's theorem is what? Mean values theorem. Okay, so the next part is mean values theorem. Okay, so similarly to the Rolle's condition, okay, we have differentiability at AB, at the open interval AB. But mean values theorem is stronger, right? So there exists a C in AB such that the first derivative of C is equals to the slope of the secant that join your endpoint. Okay, so why is it a generalization here? Because the picture that we look at here is any FA and FB. Okay, so let's say this is A, this is B, and then you have a graph that join them, right? So the claim is if you form a secant here, okay, if you form a secant here, right? The secant here. Yeah, so if you draw this secant here, okay, there will be some point in the middle of AB such that the tangent line has the same slope with this slope. Okay, the slope that joining FA and FB. So can you see where's the C in this case here? Where's the C in this case here? So let's create this line again. Copy, paste. Okay, so where's this C here? So maybe we can find C around here. Okay, so C is around here. Okay, so this is a generalization of Rolle's theorem. You can imagine that we are like rotate the Rolle's theorem. Okay. Okay, any questions so far up to here? Any question? Any question? Okay, if not, soon we will see a more generalized means values theorem later. Okay. Okay, since everyone is here, right, I want to remind those who just come in about your project. Okay, so when you do your project, right, research, don't just look for the theory, because most of the theory will already prove in class or mentioned in class. So I want you to study the theory from the point of view of the author itself. OK，从人文的角度去认识这个定理或者理论。Make sense or not? Okay, tell me how does this author think about this theory, and then why he come up with this theory? How useful is this theory? Okay, for him. Okay, maybe not for us, or not yet for us, but for him first. And then you will learn better. Okay, you will learn better why these why is this theorem got created? Yes. Because you will always heard you will also always heard people that don't understand math say that 哇这么多定理要背啊，这么多 theorem 要背啊，什么啊这样，对不对？So this is our job, okay, to study why this theorem got created, and then you can explain to your friend, 哦，他以前就是要来做这个的，来啊，something like that，这样的，好，OK， yeah, okay, all right, so any question? We have enough people here. I think we have almost. Oh, only Sydney is not here. Anyone know where is Sydney? Okay. Maybe let's discuss a bit. So maybe week 12, maybe we do a evening time of presentation. Evening time. Okay, like last time. Maybe 6 to 8 like that. I estimate around each one of you take about 5 minutes. So there are how many students here? Maybe about 18. Tuesday night, Tuesday evening. Not available. Nothing to do. Okay, just Tuesday. Tuesday evening, okay, not everyone. Week 12, maybe 6 to 8. Yeah. And then there will be one, sorry, for class. Oh, until 6. So you want to break for a while or you want to continue the break? 6. What do you guys think? Up to you. If you want to take a break, then 7 to 9. Yeah. Okay. So week 12, Tuesday, 7 to 9. Okay. There will be one general topology student join us because there's a master student they also need to do presentation. So I will just put him together to you guys. He also need to present. Yeah. So you also get to ask him questions. So it's the same as last time. We have this Q&A section, and then if you ask question, then you will get a bonus. It's similar to last time. All right, but this time is different. This time I swap the order. What order did I swap? Do you recognize? I ask you to present before you submit your project. I don't know. This time, right? I ask you to present first, then you submit your project. Okay, so why do I do that? Last time different, eh? Oh, last time is also, last time I just dragged the deadline a few days after, but this time I give you more time to do the project. Yeah. So what I want you to do is after you present, okay, maybe you think that there's something short in your presentation or you need to include it after the Q&A section. People point out, hey, how about this part? How about that part? Oh, I don't know. I haven't found it yet. Okay, go and find it. Okay, and then put it in your final presentation of your project. Okay, yeah. Does it make sense? So if you want to submit draft to me, right, you can either submit a slide draft or a project draft, depend on. Yeah. So here, whoever give me your title here, I know Jack haven't, Han Ye haven't, and then Zeri haven't. Okay, so start, go and find your suitable project. Okay, you can look inside my course information for the recommendation. And also, I put out the list of those who already chosen, those topics are chosen. So try to avoid. Try to avoid. And Seng also haven't, right? Yeah. Huh? Okay. Yeah. 只记得要记得找。好。Okay, good. Right. What time is it? 12:41. Okay, let's do new stuff today before we take a break. So we want to finish up the first derivative test with second derivative test. Okay. So in the calculus, right, what do? You find first derivative and then identify the point, and then you want to determine whether it is a maximum or minimum point. So what do? You continue to differentiate. Okay, so this is what we call the second derivative test. So what's the condition here? So let's say f is defined on a domain df, okay? And then you have a point such that the first derivative is 0. Okay, so this is the condition you have in your calculus. Then what do? If the second derivative at that point is greater than 0, then you deduce that fc or c really, so not fc, but c is a local minimum or maximum greater than 0. Now, if it's greater than 0, it is maximum or minimum? Minimum, okay, it's opposite. Okay, I don't know what is opposite means to you, but this is how I remember it. Because I think of a greater is big and then minimum is small. But depend on you how you want to memorize it. And if the second derivative is less than 0, then C is a local maximum. Opposite. So in this statement, it doesn't tell us if f c equals to 0, what happened? Okay, if f prime c equals 0, we don't know about c. Okay, nothing we know about it. Okay, so what we do is we will first prove A. Okay, we just prove A and then B is similar. Okay, B will left as an exercise. Okay, we will just prove A. So how many conditions here you need to remember in your mind? How many conditions here to prove C is the local minimum? What are the conditions? Quickly memorize it. What are the conditions for C to show C is the local maximum? Let's minimum. Let's say. Okay. What's the condition? Memorize. Huh? How many conditions you need? How many conditions you need to show C is the local minimum? How many conditions you need? 2. So what are the 2? F prime C is 0, and then F prime C is larger than 0. Okay, only these 2. Remember these 2, and then see how these 2 pop up in the proof. Okay, so remember these 2 conditions, and then let's see how this 2 condition is used in the proof. So in real life, right, you just need to check that these 2 things works, then the point is local minimum. But how it works, this live inside this proof here. Okay, so how to prove this? So let's see how to prove this. So we only have 2 conditions to work with here. Okay, so let's start with this second derivative, f prime prime c greater than 0. Okay, so what does this mean? If I already say f prime prime c greater than 0, meaning what? Second derivative exists. Okay, how can we write down this second derivative here? Yeah? What's the definition of second derivative? Sorry. S go to C such that f prime x minus f prime c over x minus c. Okay, so this thing is greater than 0. In particular, what? Again, in particular, what? In particular, the left and the right limit also greater than 0. So the left and right limit of this first derivative secant function is also greater than 0. Agree or not? Does everyone agree? Okay, if the limit to C exists, left and right limit must coincide. Agree? Okay, huh? Okay, good. So, what does this mean? So, what does it mean by left limit is greater than 0 and right limit is greater than 0? So, if you approach from the left, approach from the right, okay, both limit have to be greater than 0. Okay. So, it means what? It follows that if you find a smaller in a neighborhood enough close to C, so meaning if I found Rx such that Rx greater than 0, such that for all x in where? In, let's say we call this interval n. So what is n here? So I define it to be C minus R, comma C union C, comma C plus x. So what is this? Can you imagine in your mind what is this? So let's bring this C down here. So where is C minus R and C plus R? So C minus R should be on the left hand side. C plus R is on the right hand side. Okay, so there exists this interval here such that for all x in n, f prime x minus f prime c over x minus c is greater than 0. Can we do that or not? What do you think? Can we do that? Can we do that or not? Can we do this or not? Because of the limit property. If we cannot find this interval, right, meaning what? We can always find some point such that this secant function here is less than or equal to 0. Then how can your limit is greater than 0 in that case? Remember assignment question? Does it make sense? Okay. So at some point, the secant function have to be always greater than 0. If you cannot find this interval, then you can make your interval shorter, shorter, and shorter and shorter, right? And then found a subsequent that converge to something less than or equal to 0. Then the limit doesn't exist. This is a bit similar technique that we use in the assignment. Okay. Make sense? Okay, so there must exist some neighborhood like this. Okay. So what's the other assumption that you know about f? We know that f prime prime c have to be less than 0. And then also, what do we know about the first derivative of c? Recall. This one I asked you memorize, right? Two conditions. What's the other condition? Louder? Who remember? Yes. So meaning what? This equation, this inequality here becomes what? Prime x over x minus c is greater than 0. Since f prime c is equal to 0. What does this equation tells you? This inequality here. What does this inequality here tells you? If x live in the left interval, what does it mean? X is some number that's less than c. So what's this difference here? Negative. So this denominator here is always negative if x is living on the left interval. So for x in the left interval, f prime x is smaller than 0. Okay, so let us write down. So this implies that for every x in the left interval, f prime x is, so I mean x minus c is less than 0. So f prime x is less than 0. Okay. How about if the point live in the right interval? X minus c is always greater than 0. So meaning f prime x is also greater than 0. But last time we proved what? If the first derivative is less than 0, meaning what? The function, what does the function is doing? The function is decreasing. Decreasing. Okay. And then if the first derivative is greater than 0, then the function is increasing. Okay. Strictly decreasing and strictly increasing. So this means what? So what? So f has a local minimum at C. So what does the local minimum say? That is, there exists a, let's say, D such that what? Such that if x minus y, so such that if x minus y is less than, sorry, c minus y is less than d, then fc is less than equal to fy. Okay. So in this case here, I got c, I got what do I have? I got r, I got x. Okay. How do I find this d here? How do I find this d? How do I find this d? If I know that for c minus a to c, it is decreasing, c to c plus x is increasing. Okay. How do I find this d to show that f has a local minimum at c? Okay, let's bring this picture down so that we can read both of them together. Okay, so how to find d in this case? You know, on the left-hand side, R will work. On the right-hand side, S will work. So how do you find a D so that both sides work? Yes. So we just fix. So fix D to be the minimum of R or X. Okay. So you fix D as the minimum. Does it make sense? Yeah. Okay. Okay. So increasing means what? Increasing means, decreasing means what? Decreasing means that Fy is greater or equal to Fc. Okay. And then increasing means what? Also Fc less than or equal to Fy. Here is what? For y greater than, so for y greater than c, y greater than c, and then for this case here, for on the left hand side, on the left hand side, when y is less than c, precisely what we want. So let me write down here. So on the right hand side, on the left hand side, we have decreasing. On the left hand side, we have increasing. Make sense? Okay. So you see why we want the first derivative to be 0, because we use it in the what? In the second function there. Any question about this proof here? Question so far? So far so good. So try go back and write it out for the case of local maximum. Okay, similar. Try and write it out. So the most technical part I would say for this proof is to show that there exists some R and X here. Okay. show that there's this some R and X such that this inequality works. This is the most technical part here. Okay? It's not too obvious, but it's not hard to prove it. Okay? Suppose there's this none, then you cannot do it. And then what? Then you can create a subsequent that doesn't converge to something greater than 0. Try it. Got question? No? Any question? Any question before we take a break? Maybe we'll take a break from here before we go to generalized mean values theorem. Any question about this proof? If you want to discuss about this technical part, also can if you want. But the whole proof, I think, is quite relatively easy to follow. Okay. Yeah. Any question before we take a break? No. Okay, let's take a break until 108. Okay, then we'll resume with generalized mean value. Meanwhile, I bring some snack. You can pass around. I think he was. 为什么？哦，OK OK。在哪？它回放。他说你一定要寄到他那里。他没说啊，你如果预约。哦，你是预约，你都自己要带预约。对啊，我要去城市。你不能够去最近的梦那里有发片。好。下次下给我。华为。对。哎，然后那。没有预约。同学戴眼镜。你电话怎么了？一半屏幕都黑，根本输不了密码。所以他说就这两。他说那我带齐了。带齐。对，为什么黑这样？轻轻的摔了一次。哦，就摔。我这样摔的几个，你这个好像不是很轻。好像不轻哎。你那手机是什么东西？荣耀10。哦，认证。对。哦。对。好的。没有再来，因为我因为我父母刚从澳洲回来，然后我有带一盒回来，可是我没有说我带来，然后结果我忘记我车换几万，我就带涨下来了。现在应该明天早上带来。应该去吃吗？没有啊，我们去玩。哪里的卤蛋？大海鲜。那有蛋黄。 一直也在是。你只要某个时候你要 present 那个 video 啊，某个时候你要 present，那你这个就比较 analytic 的风格，希望你能够快快有道理。这头是，三件事来做一点比较一个人常识。好，现在多了，比我多。真的，有的，不然那咱们介绍去这儿。没有，你不要把 Chinese screen through 就好，啊，你 screen through，你看它什么时候用到这个 function。有的，不可能，不可能。已经来 screen 完这么说的，你没不知道的，是完全不是这个。那你看，你看，比如说这个，哎，我要看的是类似这种。 divisibility macam algebraic. It has an icon. Now你才会来看就它 introduce 这个 function 的时候，它肯定不是为了这个 algebra。它有我做了这个 function 之后，我没有叫你说 but from there you can run everything so 那个我们一个source 因为我自己也问题，我休息了。人重要都是这啊，我他三号应该会不想可能，那个结算是好像没有用，一般对他如果你找到有点这种吗？Okay, let's start. So again, so we'll prove okay, we will prove generalized mean values theorem. Or sometimes we will call it a Cauchy's mean value theorem. Okay, so this is very helpful for your last question in your assignment. That assignment question will ask you to use mean values theorem to figure out the Taylor expansion. Okay, Taylor expansion. Yeah. If you want to refer, right, you can look for the book. What's the book? Fitzpatrick. Okay, Fitzpatrick on the section of Cauchy mean value theorem. You can find some hint for your last question in your assignment. Okay, you can find some hint there. Okay, Fitzpatrick. You have to jot it down. Fitzpatrick. Fitzpatrick's section on mean values theorem, a generalized mean value theorem, will have hint for your last question in your assignment. They will have the hint there. All right. So what's this generalized mean values theorem here? So we'll have if f g continuous on closed interval AB and differentiable on open interval AB, and if the first derivative of x is non-zero for every x where it is differentiable, then similarly, okay, in the mean values theorem, there must exist what? Exist C, okay, exist C in the AB such that, okay, this is the part that is different now, okay? Every mean value theorem is different at this part here. So here, so previous two mean values theorem, right, only involve one function, but this time we involve two functions. And then you see, we want to require g prime x is not equal to 0. What does it mean? Always, when you see you don't want something to be 0, right? What does it mean? I might want to divide this value. I want to make my fraction make sense. Okay, so you expect this g prime here will exist at some denominator. Okay, so what's this C doing? So we will have FB minus FA over GB minus GA equals to FC F prime C over G prime C. Okay. Okay. How should you think about this quotient here? How should you think about this quotient here? Because okay, let's just think about this theorem here. You see, if I separate f and g, right, both of them will satisfy mean value theorem, right? So meaning I can apply. So let's do some analysis on this statement here. So we can apply NVT on f and g separately. Okay, so meaning what? There exists maybe C1, C2 in AB such that FB over FA, FB minus FA over B minus A is F prime C1. And also we have GB minus GA over B minus A equal to G prime C2, say. So how to get the generalized mean value theorem? What we can do is really we can divide both equations here. Correct? Divide both equations. But if you divide this both equation, it might be the case that C1 not equal to C2. Okay, if you just simply divide them. But in this statement, that C is the same or different C. The same C have to do the job. Okay. If you just simply put these two statements together, these two C might not be the same. C1 and C2. Okay. So that statement is even stronger. Again, the generalized mean value theorem is even stronger here. Okay. Okay, so what else we can see from this? Let's say GB equals to GA, what happens? If GB equals GA, what happens? 0. Right. So there exists some point C such that G prime C2 is 0. Okay. What else can we talk about it? So let's say GB equals GA is 0. You cannot divide by 0, right? Okay. But what happening actually? What is happening actually? If GB equals to GA. Mm-hmm. 0. Okay, what can we say about the statement then? What I want to claim is the whole thing should reduce to a MPT on F. And that the whole statement will reduce to a MPT on means value theorem on F if GB equals to GA. I mean, if GX equal to X for all X in X for all X in AB, not just GB equals GA. Maybe G is just a constant, not constant function, but how to say should be constant function now. Let me think. Yeah. So I mean, okay, right. So okay, yeah, I'm wrong. Just now I was talking about GB equals to GA, right? So that one surely we have there's a C2 such that G prime C2 is 0. But let's say this G is an identity function. Gx equal to X for all X in AB. Then what happens here? What happened to this value here? B minus A over B minus A. Just one. Okay, it's just one. And what? And actually for all points in AB will realize this this derivative here. Okay. So you will have FB minus FA over 1 equals to F prime C over G prime C divided by 1. Does it make sense? Okay, wait, let me rewrite this for you. So let me rewrite this. Okay. So this is first analysis. Second analysis, so say gx equals to x for all x in. Then what happened to this generalized mean value statement here? So we can rewrite the inequality here, right? So we can introduce b minus a and b minus a here. Okay. But if gx equals to x, what happens to this equation here? This factor here becomes what? B minus A over GB minus GA. Becomes what? Let's say GX equal to X here. GB minus GA becomes just B minus A. Okay. And then what is G prime C here? 1 for any C. Okay, no matter what C, it's always 1. So in this case here, the whole statement will reduce to mean value theorem itself. If G is an identity function. So let's prove it for the general case now. Okay, prove for the general case. So first of all, we want to note that the derivative, the denominator actually makes sense. Okay, meaning GB minus GA is not 0. Okay. Why is it not 0? Try and think about this. Why is it not 0? Sorry? So why? So if G prime is not 0, so why GB and GA cannot equal? Can it be something like this or not? So why? Why? Oh, good. Rolle's theorems. Okay, so what does Rolle's theorem say? Okay, as otherwise, if GB equals to GA, there exists what? So by Rolle's theorems, Rolle's theorem, there exists C in AB such that G prime C is 0. But we assume that G prime X cannot be 0 for every point inside AB. Does it make sense? Okay, so this is why this condition here so important. So let me point this condition up here. Okay. So that's why this condition is important. So I want to make sure my GB and GA is not the same. Okay, good. So what's next? So next, we're gonna use means values theorem trick. So what's the means values theorem trick? We like to define an extra function h. So how do we cleverly define this h here? So remember last time we defined the h in mean value theorem so that we can use Rolle's theorem. So this time we should be because this is generalization of mean value theorem, right? So we want to define an h such that I can use mean value theorem in this case. Okay. So what's the H we can devise here? Okay, let me ask you a flavor. Let me ask you a flavor. Do you like that I give you something and then I show you why it works? Or I tell you how it works, so I define such thing. Which one you want? One or two? One or two? Do you want like I give you something new and then I tell you how it works? Or you want me to guide you through how we get this new thing? Which one you like? Two, huh? Okay, good. Okay, let's do two then. Actually, this is a very two different philosophy in this world actually. So basically, religion is break into these two parts. I mean, these two different types. So one type of religions is you study the environment or the God. Let's say there's a God. Let's say from ourselves. Okay, what type of religion fall into this category? For example, Buddhist. For example, Taoism. All the philosophy stuff. Okay, we study natural or God using our way of understanding. What's the other way? I tell you what is wrong, what is correct, how this thing works. Okay, these kind of religions are like, for example, Christianity, Islamic, Judaism. Okay, so they tell you what is true. Okay, you don't know why one. I just told you. Okay, this is what we call a revelation. Okay, what is it revelation? How to say it? 启示, how to say? Renovation. I feel like I'm missing some syllables there. Revelation. Okay, revelation. Yeah, correct. Okay, revelation. So it's like 启示, but the other way is like we work towards it. Okay, so sure. Okay, let's use the second way. So what's the goal we want to get? So okay, so let's see. So I put a question here. How? So the question here is how what? How to define H so that we can apply mean value theorem, let's say. Okay. So the goal here is what we want to achieve. What is our goal? Our goal is to reach this equality here. Okay. Our goal is this one. Right. So our goal is this. Okay, good. So our goal is this. So what can we do here? So our goal is this. So what does the mean values theorem tells you? Can you tell me what does mean values theorem tells us? If HA equals to HB, then there exists C in AB such that what? FA minus HB over, okay, maybe the other way around. B minus A equals to H prime C. Okay, so you want to devise a H such that you get this final equality here. Sorry. What's the condition for the MVT? What's the condition? Oh, okay, good. So this one is Rolle's theorem, is it? Yeah, okay. I remember the wrongly. Good, thank you. So if H is what? Continuous on the closed boundary, and then it is differentiable on the AB. Okay, good. So this one actually includes Rolle's theorem, right? If F if HB equals to HA, meaning there exists some point such that H prime C is 0. Okay, so this one includes rows here. Good. So how do you devise H such that this is true here? Okay. How do you devise H such that the bottom here is true? Okay, you want to show something is equal, right? Something is equal. So meaning what? So you can play around with this equation here. Maybe let's work a little bit backward. So what can imply this inequality here? Okay, what can imply this inequality here? So maybe FB minus FA. Hello? Everyone see this? There's about a magic to happen. Oh. Everyone see this? There's about magic to happen. So how to get this two quotient here? What can you do? You can move one to the other side, right? Or move which one? Let's say we move this one to the other side. So 0 equals to FC over GC. Can you do this? Guys and ladies and gentlemen. Alright. Okay. But what do we know about G prime C? This thing here. For any C in between A and B, it is non-zero. Okay. Since it is non-zero, right, we can really multiply on both sides. Okay. So what can we do here? GB minus GA of G prime C. Okay, so we wrote until this stage already. So what's this thing? What's this thing here? What's this thing? First derivative of f minus, what is this quotient here? This quotient here is just really a number, just a constant only. Okay, and then multiply with first derivative at C. So what are we going to do here? So why there exists C such that this work? So can you see what's the h we want to define here? What's the h? H to be hx to be fx minus fb minus fa over gb minus ga times gx. Okay, first of all, this function here continuous at ab or not? Closed interval ab. Continuous, right? Because f and g are continuous at closed interval ab. Differentiable at open interval ab or not? The differentiable? Yes, because because f and g are both differentiable, so their linear combination also differentiable. So this h here is continuous at closed interval ab and differentiable at open interval ab. What's more? What's more? What is HA and HB? HA is what? HB is what? HA is what? Huh? What is HA? Kingston, you want to say anything? What is HA? FA minus FB minus FA over GB minus GA times GA. Okay. How about HB? What HB? Oh, let me remove this. What is HB? HB is what? FB minus FB minus FA over GB minus GA times GB. Can you relate HA and HB or not? Can you relate HA and HB or not? Seems different, huh? What do you want to say? HA minus HB is what? Can you recognize this HA and HB or not? The difference is only this FA, FB, and GA, GB, right? This number here is the same. You can see it as a gradient. But the claim is they are equal. Are they equal? Why are they equal? Huh? So weird one. Why are they equal? Look very different, or at least to me. Why are they equal? Huh? The claim is FA equal to FB. So let's take FA minus HB. B is minus FB. HB. Is here. Okay. So what do you get here? Are they equal or not? Huh? Equal. So here we got FA minus FB. So to make the denominator the same, we need to put GB minus GA also, right? And then minus FB minus FA times GB GA or GB. Huh? Let me see. So GA, yes, GA minus GB over GB minus GB. So is this 0? Is this thing here 0 or not? What's the difference between the first factor on both sides? FA minus FB, FB minus FA. So differ by minus 1. Okay. GB and GA differ by another minus 1. So minus 1, and minus 1. So you get the difference to be 0. Can everyone calculate this? Can you see 0 here? Can see 0? No more calculation. Everyone see it? Think can see 0 or not? 8? Can or not? Can see 0 here? Huh? Can, right? So you put this minus inside here, you get FA minus FB. Okay, so you agree on the first factor. Second factor, differ by a negative. Okay, so you cancel both sides. So this whole thing here will equals to 0 actually. Okay. So that's mean what? You can use Rolle's theorem here. Okay, so you can use Rolle's theorem because FA equals to FB. Okay, so since what? HA equals to HB by Rolle's theorem, there exists a C in AB such that h prime c is equals to 0. But what is h prime c here? H prime c is really f prime c minus what? Minus fv minus fa over over gb minus ga times g prime c. Okay. So you get the result you want. Okay or not? So far so good. Any question? No? Okay. So you see, when we work backward, we still need to write the argument from the start. Okay, we define first and then we show that equals. Does it make sense? No question? Any question? So the lesson here to learn is when you see the book, you see the book in the proof that say, oh, define this new function and then it works. Define this new function, it works. Okay, it's not that they come up with how to say. They come out with the idea out of nothing. Precisely, they come out of the idea so that I can achieve the goal. Okay, so you need to work backward to see why I define this. Does it make sense? But when I show you, okay, I need to give you the answer first, and then I prove it to you why it works. Does it make sense? Yeah, yeah. So this is how you should read a mathematical proof. All right. So far, any question up to here? If not, we want to go into a very important theorem before we close out this chapter here, this chapter about differentiation, which is the L'Hopital rule. Okay, we will do L'Hopital rule. Okay, so similarly to a usual case, right? We will do some example on L'Hopital rule first. But before that, I scared you. Wow, this scam number keep calling me. How? She says, wait for another agent to pick up the phone. I don't care. Okay, so right. Okay, so let's recall what's the L'Hopital's statement here. Anyone remember how you use L'Hopital rule? So let f and g are differentiable on an open interval AB that contain a point C, such that, so the easiest L'Hopital is when FC equals to GC equals to 0. Okay, so this is the easiest L'Hopital. So what does this say? We also need to require that G prime X is not 0 for all X in AB, such that, say, such that, oh, wait, I think I'm a bit stupid here already. Let's see, such that X is not equals to C. Okay, then what? Then the limit of X going to C of Fx over Gx is equals to what? Okay, if you have both of them equal to 0, what do? You differentiate the top function and the bottom function, and then you continue to compute for the derivative. Correct enough? Okay, this is L'Hopital rule, right? So you can do this provided that the limit on the right exists. So you can keep on doing it until you found your limit, right? This is what you did in your secondary school of calculus. And more generally, what you can do, the conclusion also holds if what? If the limit of x going to c of fx is equals to plus minus infinity, and similarly for your g. So you can do it for infinity over infinity, correct or not? Not just 0 over 0 for L'Hopital rule. Okay, and more generally, so here is a limit from x to c, right? You can replace this limit from x to c just by one-sided limit. So you can consider right limit of c, and you also can consider the left limit of c only. Okay, it's also the same. You also can apply this L'Hopital result. Okay. So even if you replace it by one-sided limit. Okay, so I mean, let's get some question done to refresh you how to use this L'Hopital rule. So let's say we want to compute ln x over x squared minus equal to 1. What can you do here? Differentiate both sides, y, both top and bottom y. Because ln y is 0, 1 squared minus 1 also 0. So you use L'Hopital rule. So if you differentiate ln x, what do you get? 1 over x. And then 2x for x squared minus 1. And then can you compute or not now? Or do you still need to use L'Hopital? So the top is what? 1. Bottom is 2. So it's 1 over 2. So what law you are using here? Because now you are in analysis class, right? So why can you apply limit law here? In the last step. This is limit law about what? Sorry? Yeah, property of limit law. So property, whose property? So we have learned convergent sequence, right? Continuous function, right? So this is limit law for continuous function, okay? Because 1 over x is continuous at 1. And then 2x is continuous at 1. Okay, so you can find limit law of continuous function. Hey, but there's a bug here. There's a bug here. Where's the bug? Why the derivative of ln x is 1 over x? You compute the second function, x minus ln y over y minus x. Not yet, huh? But how to compute ln x minus ln y over y minus x? How to define ln x? How to calculate ln x minus ln y over x minus 1? What is ln x? What is ln y? I haven't defined yet. Inverse of 1 over x, or inverse of e. Okay, good. So that's the point here. So you want to define it in terms of another things. Okay, so later or in the future, okay, I will put this definition into your tutorial. Okay, we will do a systematic introduction of ln trigonometry function, okay, in your tutorial. But later I will briefly mention about it. Okay, so really, how we define ln x is using the derivative. Okay, later I'll show you. We define ln x such that its derivative is 1 over x. So we want to ask what function that has derivative 1 over x. And then we define it to be ln x. Okay, this is how we define it. So the question of why the derivative of ln x is 1 over x is by definition. Okay, it's by definition. Okay, it's not true the secant function. It's by definition. Okay, later I'll show you. But let's go through the L'Hopital first. All right. What else? Maybe we have this kind of problem. Let's say limit of x to infinity. Okay, this also work. Okay, of x squared over ex. So what's this limit here? So this limit type is infinity over infinity. So we can use L'Hopital rule. Okay, so how do we use L'Hopital rule here? How do we use L'Hopital here? Sorry? Differential. So what do we get? 2x over ex again. Okay. And then do we get the answer yet? Not yet. Still infinity over infinity. So we again apply L'Hopital rule. So let me put I here if I use L'Hopital rule. Okay, put L here. And L'Hopital rule again. And then we get 2 over ex. So now, are we good? So we can use limit law of continuous function. Okay, so we get 2 over infinity, which is 0. All right, what else? Let's say we do another question on one-sided limit. And let's say we want to take limit of x go to 0 plus of xa ln x. Does this follow any limit type or not? This one is multiplication. This is multiplication. So does it follow any limit type or not? Infinity over infinity or 0 over 0? How do we view this? How do we view this? Not that a is strictly greater than 0. How do we view this? Sorry? 0 times negative infinity. But in the L'Hopital rule, we only deal with negative infinity over infinity and 0 over 0, right? Yeah, so how do we realize that one of those? Not that this x are coming from where? Coming from the right-hand side of 0, meaning what? This x are positive. Positive. And then a is also positive. So x to the power a is positive. So positive towards 0. How about ln x? What happens to ln x when you approach from right of 0? What is the graph of ln x? Go to negative infinity. So xa go to 0. X to the power go to 0. Ln x go to infinity. Negative infinity in particular. So, okay, I'll do. I can consider ln x over x to the minus a. So this is what type of this? This is the type of what type of this? This is the type. Change color. So this is the type of negative infinity over infinity. Okay, so we can use L'Hopital here. So if you use L'Hopital, what do you get? What do you get for L'Hopital here? What do you get? 1 over x over minus a times x to the minus a minus 1. Okay, so altogether, what do you get? 1 over minus a x to the minus a. So what's this? This is limit of x to 0 plus of minus a 1 over, so minus 1 over a times x to the a, which is 0. Because 1 minus a is a constant. Any question about this? No? Also, there's a bug here. Where's the bug? This a here should be any real number. So in the tutorial this week or last week, I think this week, last week, I asked you to prove the derivative for rational number, but not yet for irrational number. So why for irrational also satisfy this rules such that you can pull the power down and then subtract 1 from your power. Okay. We will do it after we introduce the exponential function. We will do it together when we introduce the derivative. Okay, I mean when we define the exponential and the trigo function. Okay, in the tutorial systematically. Okay or not? Okay. If not, otherwise, there's one way to define this irrational number. Power of x. How do you define it? You define it as a limit of a Cauchy sequence of rational power. You can do that as well. But how to show that limit exists, I think it's quite a tough job. Maybe you can try it. Okay. Otherwise, we will use exponential to introduce the irrational power. All right, so we have deal with this example of L'Hopital rule. So before we take a break, we will prove it. Okay, we will prove it. So there's a lot of things to prove in this L'Hopital rule. I mean, one of you are doing this as your topic, right? Is it Zhongyi? Okay, yeah. So in this proof here, we only will do one part of this proof. So we will only carry out the proof of L'Hopital's rule only for one-sided limit. Okay, only for, let's say, right limit. Okay, and because we can generalize this proof to left limit. Okay, so if I have left and right limit together, I can generalize. I can get a result for two-sided limit. Does it make sense? So I only need to do one-sided. The other side is the same, and then since I can get both sides, then the result for two-sided will follows immediately. Okay, by combining the two results. Okay, so this is about one-sided limit and two-sided limit. Okay. And then I also reduce the proof to just proving the easiest case, which is when FC equals to GC equals to 0. Okay. So meaning we just prove first case, the easiest case, which is FC equals to GC equals to 0. And then for the limit case, you need to do some extra work. I will include this in my lecture notes. And then, of course, you need to consider when this C is infinity, like what we did in the L'Hopital case. So if Zhongyi one, right, you can explain this other proof to us that I didn't do. Okay. So someone asked me how to get the difficult point inside the project. Okay, how to get, I have a slot for this difficult point, right, in my assessment, the marking criteria. So how do you get difficulty points in my marking criteria? So if you want to get that point, you need to do something extra than what I did. Okay, if you just can say what I did, okay, explain what I do, then your difficult point will be lower. So you need to show me your maturity in mathematics. You need to tell me you learned something new by yourself. Then you will get the difficult point in the section. Does it make sense or not? Okay, so you need to tell me you learned something new, okay, that I haven't taught you yet. Okay, even better if I don't know about it. Then surely you'll get full mark in that section. Okay, but as what I would say design, that point is not too many points, so I wouldn't pressure you to say, or you must produce something that I don't know. Okay? It's just that if you can do it, I can give you the point. If you can't do it, then just some maybe 1 or 2 mark missing. That's all. Okay, or not? Does it make sense? Okay, because we need to differentiate good students. Okay, so let's prove the the easiest case, and then we will take a break. So, what's the point here? What's the point here? What's the point here? What's the point here? What is the point here? You see, fx over gx, f prime x over g prime x. So you want to relate these two things together. Just now we have a tool to relate these two things. What is that? Cauchy mean value theorem, right? So what does Cauchy mean value theorem say? Fb minus fa over gb minus ga equals to f prime c over g prime c. Okay, I mean, let's write it down here then. So let's write it here. So let's do some analyze. So what's the two we have? We have FB minus FA over GB minus GA equals to G prime A over, sorry, F prime C over. Okay. Yeah, so what's the idea here? So you see, there's two C here popping up. So let's say we don't want this to be C. We put it something else. Let's say D. So there exists some D in A. Yeah, we don't want to confuse. We don't confuse the C and D here. So what's the difference here? What's the difference here? What's the difference here? Here got difference. I mean, the difference I say here is the mathematical difference, right? So here is FB minus FA, but here only got FX. Now how to get rid of one of the term inside here? To get rid. How to get rid? How to get rid? What do we know? FC and GC is 0. FC and GC is 0. Okay. So let's say we want to do which limit? Let's say we do right limit. Okay, we're going from right. So let's say we're doing for, let's say for x going to C plus. Okay. What do we have here? We have fx minus fc over gx minus gc equals to sum, okay, equal to sum d, such that d is in between where? D is in between x and c. Okay, so if you like, let's draw out this picture here. We have c, okay, my x is going from the right, and then there exists some d here. Make sense or not? Okay, but we assume that fc and gc is what? 0. Is 0. So by assumption, the difference becomes simplified. So we get fx over gx equals to f prime d over g prime d. Okay, so what is s and d here? Remind yourself, what is s and d here? X is some point coming from the right of C. D is also some point coming from the right of C. But how we get this D? For every X, I get a D that is less than X. This is what mean values theorem tells you, right? you have a point in the middle of C and X that realize this means values, generalized means value theorem here. So if I take this limit, this X here, limit to C, this term limit to C, does this D also limit to C or not? Yes, right. Because when my X approach C, this D here is getting even closer to C. Does it make sense or not? Does it make sense? You know what am I talking about? So if I have x1 here, means value theorem will give me a d1. If I get closer, let's say x2 here, then mean values theorems will apply on C and x2, and then I get a closer d2. Make sense? Okay, so what do we have here? So we have that. So this implies that limit of x go to C plus of fx gx is equals to limit of x to C plus fd gd, which is equals to limit of d going to C plus f prime d g prime. So L'Hopital rule says that the limit of fx over gx is equal to the limit of f prime d over g prime d when d go to the same place when x go to. Hello. No question? Question? No question? No. Do you see we get this L'Hopital here? See, this d is a dummy variable. You know what the dummy variable means? Dummy variable means I can just replace the d such that the statement still hold. Is the same statement, equivalent statement. Okay? I can just change d to x. But at this point it's different, you see. This point you cannot change. Okay, before the last point you cannot change because limit for x, but the function is on d. But at the end, all the limit and functions is in terms of d. Okay, so I can change. It's a dummy variable. Does it make sense? Okay, yeah. So you see, from here we can get the L'Hopital statement. Understand or not? Any question? Question clear? Is it clear? How L'Hopital pops up? So what's the main tool we use here? Tell me, what's the main proof we use? Main tools we use in this proof? What's the main tool? Tools is 工具 TOOM. What's the main tools? Cauchy mean value theorem, and also the condition on at the point FC and GC equals to 0. Because you L'Hopital, remember in the L'Hopital rule, what's the limit type you can apply? 0 over 0. So what's the use of that 0? To get rid of the term inside your Cauchy mean value. Yeah. So for infinity, how to do? There's some tricky part it comes in. Okay, we don't want to discuss it in here because not very enlightening. I will include it in the proof. If can, maybe Zhongyi can tell us about it in your presentation. Proof for the case where FA, FC, and GC is infinity. Yeah, if you can. Okay. Yeah, you can do some change of variable like that. Yes. Yes, you can do some 1 over t, 1 over x change of variable. Yeah, something like that. Yeah, something along that line. Yes, and then you can reduce to this case. Correct. But still, you need to deal with some technicality. It's quite troublesome. Okay, any question about L'Hopital rule? So why we discuss this proof here? Because this is an application of mean value theorem. Okay, application of mean value theorems. Okay, and then the other application is the one that I give you in the assignment. Is the Taylor polynomial. It means this generalized mean value theorem will give you Taylor polynomial. So Taylor polynomial is the last thing we will learn in this course. And there's only about 5 weeks left. Okay, and then we have to finish this course. So the plan is we spend about 3 weeks on integration and then 3 weeks on sequence of function, and then we'll finish. Then. By right today we should finish differentiation. So okay, so far any question or not on this L'Hopital rule? Any question? Okay. I don't expect you to understand all of this now, but you need to go back and read again. Okay, read the lecture note again. But for now, what you need to know is what I have been using. So you need to at least know that Seng is using Cauchy mean value theorem to prove L'Hopital rule. But it's okay that you don't know what's the whole process. But at least you need to get the idea first. Okay, then later you study, how does Cauchy mean value theorem get used in this proof? Does that make sense? Yeah, this is always how you communicate or how you do work. Okay or not? OK 吗 ？OK， 理解可以慢一点来，但是你一定要听清楚人家在讲什么。OK 吗？因为很长人他没有听清楚人家讲什么，那就去做吧。非常长，他就是做错的。OK， 比如说我们这种做教书的，比如说私营做那种教球的，对不对？没有看到那种球员啊，你叫他做一个动作啊，他还不懂做我们动作，他就一直做，然后你就讲错啊，动作错啊，对不对？你要听懂教练讲什么，对，不要随便甩你的手，不要随便甩你的眼，对，听清楚的 ，OK， 等听清楚了，不会做 ，OK， 我们研究怎么做，对不对 ？OK 好，这样才会比较 effective。Does it make sense？ OK 啊，说很重要啊，在我课听清楚我讲的，然后再研究。Okay, so let's take a break until 2:20. Okay, and then we will comment about definition of logarithm and trigo.
这个
我想想，我把这个
没东西。
看多。
应该是生病了。
谁生病？生什么病？什么？
有非要讲述，但是有非要讲述，还没有。他也是怎么样？然后也在那个没有，他也是 T。
太冷吧？就是早上起来一大堆。啊？
哦，你不知道。啊，
这多少钱？
哪个？
忘记了。把那个 mix 来。
你不觉得冷？
我喜欢冷。
哦，我在马来西亚基本没有出过去。
我是没有当过去。那没有下雪。
高三对现在
高不下雪，我们这里的高下雪，不会下雪。
不会，我们这里高三也没有下雪。为啥你主要是比较高三？那我们这里高三讲，他们看到是第一个。啊，这个我还很奇，确实，确实就很。但是要排名，但是要排名的，对，第一次也是第一次排名，因为出题的，我们是那些冷到你要排的，慢慢来，我已经讲一直处理，所以天气是。
我
了解。
几点 break 啊？忘记了。有冇票？抢到了。可是看得到 option 吗？有看到 option？ 剩什么票？
傻逼哦！傻逼！
Okay, right. So how do we define a logarithm function, trigonometry function? Like, how do we explain? Differentiate log we get 1 over x. Differentiate cos we get minus sine. Differentiate sine we get minus cos. And no, just cos. Yeah. How do you do that? If you want to use the definition of derivative, what do you need to do? You need to compute the secant function. Sine, for example, for sine, you need to compute sine y minus sine x over y minus x. But what is sine y sine x? So we need to first define sine and logarithm first. Okay. So the claim is the natural log function on x or fx equals to ln x is the unique solution to f prime x equals to 1 over x for all x greater than 0 and f1 equals to 0. So we solve it like a ODE question. You learn ODE, right? Okay. So we define it to be like that. No need to ask me one. Okay, we define it to be like that. The derivative of ln x is 1 over x. But there's a question here. There's a question here you should ask. Why exists? First of all, this is the algebra question, actual algebra. Why exists? Existence problem. Second, why unique? Uniqueness problem. So you need to solve these two problems. Given this ODE question here, you need to solve why exists, why unique, why unique, why exists, why unique. So by proving existence, I will tell you that how does this ln look like? How does this ln look like? Once I prove uniqueness, then it makes sense to just mention the natural logarithm function. There's only one, log x. Not log x, not different x. Okay, it's just log x. Okay, so you need to solve these two problems here. So let me write down here. For the definition to make sense, we need to solve the uniqueness and existence problem for the solution. Okay, so for the existence of this proof, a bit tricky. We need to use integration actually. We need to use integration. So what's the integration we're gonna see here? If you assume the calculus knowledge you know first, maybe we need to define ln x to be integration from 1 to x of 1 over x. So let's say 1 over y dy like that. This is the definition of ln. Okay, we can check it. I mean, let's do it more rigorously in the tutorial. Okay, now I will tell you the story first. You can just listen. Okay, no need to check anything. I will ask you to check in the tutorial. Okay, so we define this. This is the existence part. How about the uniqueness part? Why, if this solution, if this satisfies the solution, this is the opinion. Uniqueness, there's only one way to do it. In abstract algebra, how do you do uniqueness proof? Suppose there are two solutions that satisfy this equation here, and then check that, maybe check that their difference also satisfy this equation, and then if the difference satisfy, then okay. Really, you need to use there's one property here called the let me show you. I want to write down here. Let me show you here. You need to use this identity criteria check, which is the constancy theorem that we proved last time. So let's see what is this. So let's say you have a different function is equal to 0 if and only if the derivative is equal to 0. Okay, and if everywhere, and at some point this g is 0. Remember how we proved last time? What did we prove? We proved that if f prime x is for every x in the open interval AB, then this fx is constant. But here, what do we have? Extra condition here. You know that there's one point, this f is 0. So since I already proved that the f is constant, right? And then one of the point is 0, meaning what? Every other point is also 0. Because one point is 0, and then the whole function is constant. Fx equals to fy for all xy. And then one of the xy is 0. So 0, 0, 0, 0, 0, all the way 0. Okay. So you can prove that if the derivative is 0, and then at some point it's 0, and then that function have to be equal to 0. So in the case just now, you assume two solutions. Maybe you take the difference of the two solutions. Okay. And then you see that their derivative is equal to 0, and then there's some point it is equal to 0. Then that solution, maybe let's say f1 minus f2 have to be a 0 function, then proving that f1 is equal to f2. Okay, so the whole process I will lay out in the tutorial sheet. Okay, so you can follow the flow and then see how we define it. And then very special about this long function. Long function satisfy what kind of property? Do you still remember? Long function. For example, long A, B is what? Long A plus long B. And then long A to the C is what? C times long A. Hey, where did this property come from? Where this property come from? You cannot just define it like that, right? So actually, when we define it, the derivative x1 over x, this property will actually pops up. They will pop up immediately. Okay, so the claim here is, let me read together with you this one. So if f satisfies the differential equation that we write down just now, then the solution will satisfy 1, 2, 3 property. In particular, 1 and 2 is what we mentioned just now. Ln AB equals to ln A plus ln B, and then ln A to the R is R times ln A. So we prove this property just by using that the derivative is what? 1 over x. That's all. Okay. You want to see how it done? How it get done? So let me show you one of them. Okay, let me read this book together with you. All right, so let's say we want to prove 2. Okay, how to prove 2? We want to show that FAR equals to RFA. Okay. In other words, what we can prove? We can prove that FAR minus RFA equals to 0. This is also one way to prove it, right? Okay. So that's why we set hx equals to this difference first. And then the goal is to show that this thing is 0 function. But just now, there's an identity criteria that we posed just now. How to show a function is 0? If the derivative is 0. If and at one of the point, this function is 0. So you need to show these two things to show that this h is a 0 function. Okay, so first thing to show, which to show first? Okay, he showed that f prime x is 0 first. So how to show f prime x is 0? So you differentiate. Okay, you differentiate your h. How to differentiate your h? So we assume what? We know the derivative of f prime because why? We define the derivative of f to be 1 over x. So if we differentiate f xr, what do we get? What do we get here? 1 over xr, correct? 1 over xr. 1 over xr. Where is 1 over xr? He look a bit different, but let's continue first. If we will have 1 over xr here, okay, sure. Let us write down and maybe we can compare. Sometimes this solution work quite fast, so maybe a bit hard to follow. So let us work together. How to read this book? Okay, how about let me do this? Actually, I have this book. So let's pull out this book from my iPad. Okay, what's this book? This is fixed spectrum. Okay. I'll show you how I read the book, so that you can learn and read books yourself. All right. So so for the first part, okay, what do we get? We get f prime of xr. Okay, and then the second part, r is a constant, so I get f prime x. Okay, and you see, f prime xr is what? Actually, it's a chain rule. Actually, it's a chain rule. Okay, so how to do chain rule here? How to do chain rule? You differentiate the whole thing. Okay, and then you differentiate the thing inside. So inside is xr. So you differentiate x to the power r is r times x to the r minus. So still ask yourself, what is r here? R here is just rational. Okay, this part we prove in tutorial. Okay, we know how to differentiate this. How about the next part? We get minus x over, minus r over x. So all these two put together, what do you get? You simply get r over x minus r over x. So the derivative is 0. So how far away to show this h is 0 function? You already showed that the derivative is 0, right? Meaning this h is a constant function. But constant function could be Constant 1, constant 2, right? Constant real number. But you want to show that it is constant R, meaning what? At some point, this function has to be 0. So at which point h is 0 in this case? At which point? At which point h is 0? You recognize? 1. Okay, so let's try. What is h1 here? h1 here is f1 to the r minus r times h1. Okay. What is h1 to the r? Which is h1 first, right? Okay. h1 is what? By definition, h1 is 0. So we call this a boundary condition, right? At the boundary 1, what happens? So it's 0. So first terms you get 0. And then the next term you get what? Minus r times 0 as well. So you get 0. So at the point 1, h is 0. So it's a constant function. And then there's 1 point 0. So it's a constant 0 function. Make sense or not? So you can see that what property is this? That you can pull down the power, okay, power of the number to the front of the lawn is the property of its derivative. Okay, does it make sense? Yeah. So similarly, you can prove the what is that? Not additivity and also not multiplicative. So FAB equals to FA plus AB using the same technique. You can use the same technique. Okay. I will put it into the tutorial and then you guys can try and work it out. Okay. Yeah. Does it make sense? Got question? Got question? How we got question? Last time you was interested in the trigo, right? So similarly for the trigo function, right, we need to look at a different ODE problem. So the difference ODE problem here is what? Let me show you. It's this one. Is it this one? Not this one. This is the exponential one. For the ODE, sorry, for the trigo function, it is a function that satisfies this kind of property. Second derivative plus the function itself is 0. It's true. Think about what is sine. Second derivative of sine is what? Minus sine. Minus sine plus sine is 0. Cos that? Minus cos. Minus cos plus cos is also 0. So sine and cos both satisfy this kind of ordinary differential equation. But what's the difference between the boundary condition here? For cos, one is cos 0. 1. But sine 0, 0. So the difference is the difference at the boundary condition here. Okay, so the difference between sine and cos is the boundary condition. They both satisfy the same differential equation, but boundary condition different. They start different at 1. So that's why when you draw cos, you draw like how you call the shape, like a cup. But when you draw the sine, is a normal way pattern. Okay. So similarly at f prime 0, they are also different. Okay. So this, you see, when I evaluate f at a point, evaluate f prime at a point, we call this a boundary condition. Okay, because we want to check what happened at the boundary. Boundary of what then? Actually, they are the boundary of some interval. Okay, let's say 0 to 2 pi, for example. Okay, 0 to 2 pi. So you can change the boundary. Change the boundary like what? For example, how do you change the boundary? If you change the boundary to, let's say where? Pi over 2. Okay, so for cos pi over 2 is what? Yes, 0. And then sine pi over 2, 1. So you see, when you shift the cos and sine function by pi over 2, you are like changing interchange sine and cos function. Remember? You get what I say? Let me draw it to you. Okay, let me draw it to you. So let me draw this to you. So you see, so cos is like this. Okay. Pi over 2 is here. And then sine is like that. Okay. Sorry. Cos and sine become the same. So if I shift by pi over 2, what do I mean? I start my graph at pi over 2. What happened? The cos graph here become minus sine graph. No, become minus sine. But sine graph here becomes what? I draw too far here. Okay, sine graph here become a cos graph. Okay. So if you change the boundary condition, if you change your boundary condition, your f will change. Okay, this is my point. Does it make sense? Actually, these are all DE, all DE stuff. If you want to recall. So similarly, you need to show for existence and uniqueness. How to show existence? Any idea? How to show existence here? Any idea? How to find some function that if you differentiate 2 times, you add together is 0. Where to find it? Where to find it? Don't know. There's one hint I give you. What you have learned in calculus 2. Sum of what? Taylor expansion on cos. Remember how we expand cos? One plus x squared over 2 factorial plus x to the power 4 over 4 factorial, and so on. The even power. Okay. Then infinite sum, you can do term by term differentiation. This is what I asked you to prove in the tutorial. I mean assignment. What's wrong with this number? I say hello only, please hold. If don't hello, it doesn't point out. Is it? Okay, you lang open. Okay. So you have this Taylor expansion of course. Okay. You can do term by term differentiation, right? So if you differentiate twice, do you get this thing showing to you is better? So let's say consider. Okay, let's make another booklet here. So consider fx equals to 1 plus x squared over 2 factorial plus 4 factorial plus so on. Can someone check if there's any sign change in between, alternating sign? I feel like there is, but okay. Any sign change or not? Any sign change for Taylor expansion for cos? How? How to change that? I can guess, but let's see, Got sign change or not? Feel like it's here, 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 somewhere like this. How is the sign change? How is the sign change for Taylor expansion of course? Check, 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 check. You look at me, I look at you, we also cannot get it. Correct? Okay, so how do we put this formula down? What is -1 to the power 1? Power. So what I meant is, if I write down this formula here, what is this formula? So n equals to 1 to infinity of x to the n over n factorial. So actually here is 2n, right? 2n. And then what do I put at -1 here? What's the formula here? N -1? N -1, let me think. I think n -1 works. N -1 works, right? When n equals to 1, it is 1. When n equals to 2, it is -1. N equals to 2, it is equals to 1. It's 1 minus 2 is not quite. Wait, let me think. Huh? Just n? Cannot, right? N. Oh, I know. I mean, we start at the wrong place, right? We start with 0. 0, then n will work. Is it? Okay. Okay, good. So what's the second derivative of this guy? If we can differentiate term by terms. We simply get 2n of, let me think, 2n times n minus 1 times x to the 2 over 2n. Right? But where do we start? Where do we start? Does it make sense to start at 0 or not? The first term you differentiate once already disappear. The second term you differentiate twice, does it disappear? Not disappear. No. Let me think. So differentiate once you get 2x, differentiate twice you get 2. Okay, correct. So what do you get here? So you get some term starting at 1, and then if you simplify the right hand side, what do you get? You simply get x to the 2n minus 2 over 2n minus 2 factorial. Fair enough. Where? Which part? Oh, you mean we need to swap this -1, right? So swap to +1 or -1? Think. Huh? -1? Yes, -1, correct. Because now we start with 1. Good. Okay. Because now we start with 1. Okay. So the claim is if I add this 2, we get 0. Is that true? So I mean, when you sub 1 into this value, right, you also get x to the 0 over 0 factorial. Okay. And then we can rewrite this sentence, right? How do we rewrite this sentence? I can really start with 0, such that I get x to the 2n over 2n factorial. Is it true? True. Okay. So you see, what's the difference between f prime prime x and f prime? They really differ just by a -1. So if you add them together, you get 0. They'll cancel out. Okay. If you are not familiar with this infinite sum, I suggest you to write down every term like first few terms, and then see how they differentiate. Okay. Okay, any questions so far? Any questions so far? What time is it? Okay, 2:47. I think, okay, maybe we don't go into integration, but I want to give you some idea of integration, and then tomorrow we will go into it. So what's the idea of integration? So in fact, what we will introduce integration is we will start with the Boole integration. So the Boole integration is the one that you see in calculus, which is using the upper sum and lower sum. And then this is, I think this is the project by Seng, right? Okay, so you talk about the Boole's integral. Okay, so what's the Boole's integral about? So it's very easy. Okay, we start from primary school. Okay, what did you learn in primary school? Length times width is what? 长乘宽面积. Okay, so we start with a very easy 面积 of a rectangle and the width. Okay, 这种普通的我们会算，但是呢，如果我教你算一个这样的面积，你会算吗？有点难。OK， 有点难，但是呢，不是说做不到，数学就是这样，难的东西我们才要去做，不难的东西不需要我们做。OK，so how to do? How to do? You should imagine you take rectangle, take your rectangle and then stick on your area that you want to compute. Okay, see how many rectangle you need to stick so that you can fit your area. Does it make sense? Make sense or no? Okay, so you need to fit how many area. So you think I ask you a question? If I just calculate this 1, 2, 3, 4, 5, 6 rectangle, is it enough or not to compute the area of this thing here? Is it enough? Not enough, right? I haven't finished covering the small part here. I haven't finished covering the small part here. So what to do? Rectangle. I can use more rectangle. What do I mean by more rectangle? I cannot use the same rectangle already, man. So what do? I need to use a smaller width rectangle. Okay, maybe I can use a smaller width rectangle like that. Most probably. Okay, I can use a smaller width rectangle. Then I similarly covering more area than the larger width, but still I am missing some of the part. Okay, still I'm missing some of the part. Then what do? I make this rectangle infinitely small width. Can make it infinitely small. Yeah. I think we still have time. I can go a bit further. Let me go a bit further. The other way, what you can do? 有些人是这样的，有些人是这样，他喜欢做到够就好了。但有些人呢，喜欢做的多一点。Okay. So what can you do? You can use a longer rectangle to estimate it. So let me do it now. Okay. So let me do it here. Get rid of this thing. Go a bit further. So you can use a larger rectangle so that you don't go too much away. Something like that. Maybe. Okay. Something like that. Okay, you can use a larger rectangle to cover your space. But larger rectangle means what? You overcount your area. So where did you overcount your area? So maybe this part you overcounted, and then this part you overcounted, the other part you overcounted. So the blue part is the overcounted. So what do? You also do the same thing. You make more rectangle. Okay, you make more rectangle so that you can miscalculate less overcounted area here. So for example, maybe I use this one. Okay. So here, what do I do? Here, maybe go to this side here, this side. Then this side go a bit further down. And this one also like this. And this one go down a bit. Okay, then I will have less overcounted area here. Does it make sense? Okay. So similarly, I can do it for, this is what we call a upper sum. Okay. And the other we call it for lower sum. You count from bottom part, okay, lower part. If you count from the top part, we call it a upper sum. So when we will say that this graph here, let's say this function here is integrable if the top part here is defined by a function. Okay, so this part described by a function, then the area under the curve can be calculated if this f is integrable. Okay, we'll say it is integrable. So when is it integrable? When this upper sum and lower sum will coincide. Okay, if this two sum is equal, then there will be the same. So this is what we call the boot integrable. Okay, but normally you heard Riemann integrable, right? Riemann integrable. So these two ideas actually are equivalent, but Riemann integrable is a bit different, the definition, and I think Jingsen is doing this topic. And also, I think I will ask you to prove equivalence between these two in your next assignment. I'll guide you. I'll put some guide, and then you need to see how they are equivalent. Yeah. Okay. Any question before we break? If you want to have a read before it, the equivalence between Riemann integral and the Boole integral, you can go to Wikipedia. And I will set out the assignment questions so that you can do it step by step. Okay. Why are they equal? All right. Any question before we break? Oh, we'll see you tomorrow.